So once we impose this new relation, so first, in the new quotient group, we have treated the image of G1, because it has all the roots with it. But now we have a new presentation of the elements. And then, because now we can assume that we have also of the form sum will be W here and part of a relation, or it could be other one. It could be, this is a standard form, here is a part of a relation, and here is a part of W, plus minus 1. And because it is so short, we do not care what is the measure of it. It may be all the W but one letter. It is minuscule from our point of view. In any case, we have a new canonical form, which we have this lambda semi-canonical word in rank 1. So now, when we take our next word G2, then its image in this quotient group, this will be actually in the group F over N1. We enlarge the normal subgroup. We started with F over N.
In the semi-canonical for in rank 1, you said that less than or equal lambda, this new relation, yes?
Yes.
This new relation as a whole. Yeah.
This is the new relation imposed when we go from F to N to F over N1, and then all its consequences that we knew, and then we take also the corresponding lambda semi-canonical form in rank 1. And then we look on this element G2.
Yeah, just when you impose the condition, just technically, you look only on the K part, or you also consider W1 as part of it?
Of course, we can now amalgamate it.
No, I understand, but when you consider semi-canonical words?
When you consider semi-canonical
Rank
words,
1.
we now to have, okay, we have to first define the chart of the word in rank 2. When we have the chart of the word in rank 2, first we have all the previous standard parts, but now such a thing we also consider in the chart 2, because in the chart of rank 1, because in the chart of rank 0 it was non-existent. Because this was the standard part, and this was not standard at all. Here, because we looking on the chart in rank 1, then it makes sense. And it is lambda semi-canonical if these parts are, again, there's a lambda, or W stands, maybe this is standard part, this is something less than lambda, and this is a part of W, just a final part of W1, etc. So then we consider this new chart in rank 1, corresponding we have the notion of a semi-canonical, lambda semi-canonical word in rank 1, and then we consider for G2 the word that presents it and is lambda semi-canonical in rank 1. So let me call this word W2. So W2 W2 is a lambda semi-canonical word in rank 1 that presents G2. But by the way, it may be equal to 1. We don't know. It could happen that G2 belongs to N1. Then we don't need to treat it because all the roots could be equal to 1, for example. Because we have to at the roots of all these questions.
Yes.
If the word is 1, we can take the solution of the root as 1, for example, and then we just skip over,
Okay.
if we need. But now, again, we take a equation W2 is going to be equal to some u of alpha of K2, beta of K2, where again this element is in this some group I, 0 or m, depending on the order of this element. And then, of course, we assume that all the elements in this appropriate group are much, much bigger lengths than W2. Again, the same idea. So in particular, it may be some inside word, it has inside some appearance of W1, etc. So we take the same. So then we actually proceed further to an arbitrary round. Now is the question why this construction works. So to do this, we have to consider a one-Campbell diagram in some rank K. Consider one Campbell diagram in rank K.
Maybe we could change the letter.
Hmm?
Don't K is not good because you used it before.
I did it. Did I use it?
Yeah, you did.
Four groups.
Whatever. Actually, for the rank, we need K. That's the OL. Or R. Or rank. Okay, whatever. Now, what happens? All of these relations, what we take them? So, first, we have this word WR, which is a semi-canonical in rank R, is in rank R. So it has, it appears somewhere in this, with this group WR. Then we have standard pieces of the corresponding group K that we added in this case for this element. And then these are the relations in which it is involved. For the particular, for this rank R. So we take all the elements that are equal to 1 in this group. And with all the previous all these previous relations of the same kind with ranks R minus 1 to 1 and 0. Yes, 0 is just this relation that's produced by embeddings of this group in the group F over A. Now, then, when we look on the same idea, taking of the sequence of derived one-Campbell diagrams. So we consider the sequence of derived one-Campbell diagrams. again, we need to prove yes, that actually any region in these derived diagrams have many neighbors. Many neighbors in the same way that we stated it earlier. If it is of the same rank, then, or if they are neighbors of the same rank, then should be many, I mean at least 9 of them. And if this is one region of the higher rank and the rest of the same rank, then it should be at least 5 of them. Just the same conditions that we need that we can proceed further with the sequence of derived uncoupled diagrams. Here, again, everything boils down to what happens between these two diagrams. Here the situation is very interesting for the following reason. So when we take this one, what happens standardly that we had a situation when this is a common boundary, this is the previous areas in the derived maps. Now and then we have here, say, 2 regions here, 2 regions here, whatever, and then we have here the sequence of supposed maps. All these maps, all these regions would be in between 2 big diagrams. Now here happens the following. This just cannot happen. Why? Because each of these regions has big standard parts. At least 2 standard parts. Because it's some W maybe, and 1 and 2. This is, at least they have 2 standard parts. Now, the standard parts, so, and then when they meet this region, and what happens? If it meets here just the standard part, they're extremely small, no more than 1 letter of B. But it may be that on this side it meets some W. The W was semi-canonical. Semi-canonical meant that it has semi-canonical means that it can have no more than semi-canonical means that this word actually have the canonical means at most 1 standard part and 2 parts on its side. Now, then on the okay, and when it meets this, because this is a lower rank, then this will be a very small part of this relation. Because this one, just a moment, so let me see itself. Okay. So, all these relations are of the following form. They have standard parts of the appropriate word, then of appearances of a definite wi or its inverse, and the rest are, it may appear in several places, and the rest are standard parts. Because these are the relations for every step. Because for a they are in a particular group when identified is W with elements of particular group Ki. Now, then it just have not enough place to appear here. Because these are very small parts of it. Now, this will be on this one will be or higher around this, or higher around this one on both sides. Now, then so the word here, so I mean that these parts of it are a very small part of this relation now, and then when we take the rest of it, it cannot have a common part with this except for few letters on both sides. Then just that it have not enough place to appear here. And this means that this what is called the contiguous diagram immediately generates into a direct contact. This is a
or contact with one cell, right?
Huh?
I mean, or contact with one cell. If we have one cell of lower rank between parts of bigger rank, it's possible.
Excuse me, please.
I mean that it looks possible to have one cell of smaller rank between two parts of bigger rank. I mean, one. No, and then directly after that there are no meeting. So they have one cell and then they go in different ways.
No, here on the end of it there may be, but in between.
But in between, yes, right.
In between there could be only direct meeting. Because every cell of smaller rank, it must have the biggest parts of it are just standard pieces, and standard pieces may not have common parts with both of these sides.
Oh, right.
Because each of these should be a small piece. Small piece is no one letter
Yes.
Y. So that it means that the contiguity diagrams collapse into a direct meeting. Now, but the direct meeting also could be also very short for the same reason, because the standard parts of it, there are different standard parts unless there's the same relation. If the standard parts are the same, then we just have a common relation, then which just can take a smaller number of regions representing the same element. Therefore, it is very small, and this means that it means that in general, when we look on the common part, it is very small. And this argument goes throughout for every rank, because from the beginning we have taken all the standard parts very much different one for another. And the W's which we use here are much smaller than the appropriate standard part, because we have chosen such embedding that our W, whatever rank we have done, is much shorter than all the standard parts that we use in the construction of appropriate group Ki. And so then we immediately have, and here this argument is much easier than in the case of Burnside group, and certainly much easier in the case of the Engel group. The whole problem is how to deal with the contiguity diagrams. And here immediately we have the collapse of the contiguity diagram, because the relations are made from standard parts with no being able to come together, and then this diagram becomes highly hyperbolic. Each one has a lot of neighbors. Then it means.
So the point is that the contiguity diagram is always a direct. It's a
direct meeting.
Direct coordinate.
Yeah, and the direct meeting could be very short, because this also have the standard parts of it, and the standard parts have different exponents of x.
Doesn't fit.
Yes, it doesn't fit.
Yeah.
Just by the construction
So
of
the opposite to the Burnside case, where
no, for opposite, no. Now, no. For the Burnside case, we could eliminate the contiguous diagram, but taking the canonical form. And then when we analyze the contiguous diagram in the Burnside case, because on the both sides we need to have the canonical form, then without some regions on this boundary should be the same, because the canonical form is actually built having the same decision problem on both sides, so it should coincide, and this results in the collapse of the contiguity diagrams. But here it is much easier, because it is just built of bricks that do not fit. Therefore I said that why we actually need just a higher rank small iterated small cancellation. But when it comes to the considering the derived sequence, or the sequence of derived diagrams, that is very easy. At this point, just we cannot have any continuity diagram between them.
yeah.
Okay, so this is the point. Now, how we use it? Then we just know. So we know. Then when we compare now the two words which represent the same element in the group, in the rank, but both of them are lambda semicanonical in certain rank R. So it means that it may be only one standard part and pieces of standard part on its sides, or one of them could be appropriate W, which is also very, very short with the opposite pieces. Now, and then we have a similar chart of rank R for the second word. We know that both words represent the same element in the group. So it means that if we glue them together, so we have a relation. Because then this will be equal to 1 in the Gaussian group. In this case, it will be group F of NR. Then we can fill it in with a R, with a Rankapel diagram of rank R. And look what happens here. Now then, if we have standard arcs here, so they should be part of a relator, because it cannot be cancelled out. And then it means that the only way that they are equal is we have here exactly another relator here, such that we take the complement of it on this side and complement on this side, such the whole product is equal to 1. This is the only way that different lambda semi-canonical words in rank R may represent the same element of the group. But then when we transform this, then we obtain a similar picture for smaller rank, etc., etc. Because when we reduce it from this, the regions of rank R, so the problem reduces to the regions of rank R minus 1, and then it just descends to the equality. So we have a very clear way to see when elements present the same element in the group. Okay, and this means that when we have seen this group, we just take this the inductive limit of these groups for all R. So the resulting group will be a quotient of the original group. Of course, it is finally generated because we proceeded with all the elements of the group which we enumerated in advance. So each of them, either it was one, but then we could skip over it, or we just added a relation that gives all the roots of all the equations, etc. So this, in short, shows the construction of this group, and the main part of it was when we consider the sequence of derived Van Kampen diagrams, because the contiguity diagrams collapse, so it is hyperbolic. And then all the geometric consequences are false, except for example, in the way that I presented here, when the words are equal, when we look on their chart in rank R, and then if they present the same word, they should correspond in this way. By the way, one of them might be just W, but the rest should be standard. And then this should be equal to 1 is appropriate group. So this is finally the construction of this superdivisible group.
So in this kind of sense, to construct a divisible group is
Just to take the cyclic groups, just to extract powers. Yes, here we can extract generalized powers in essence.
so we can resolve it. I mean,
It's not a hyperbolic group. What did you say?
No, of course not. We start in any group. No, but in a sense, we deal with it just in a way that it is amenable to treating as a generalized representation.
so I'm trying just to realize how this construction can be related to the conjecture that the PSO2C is superdivisible.
No, because no. You see, it's an entirely different idea.
No, I
Because
understand.
this, after all, this is a very artificial cognitive construction.
Here it is.
Yes, your PSL exists in nature.
Yeah,
What's the connection that what PSL to C?
yes,
That this is a
yes, it's superdivisible.
People that deal with this firmly believe it is superdivisible.
I don't know believe, but anyway, it's not, visible something, visible against the conjecture.
for any. Okay.
So
For any particular rate, it's possible to check it. Yes.
for any, but it's not ring. It's C.
I don't understand, but for any, check that any.
Particular word.